Now that we understand how DES works, let's look at a few attacks on DES, and we're going to start with an attack called Exhaustive Search. So our goal here is basically that given a few input-output pairs, MI-CI, our goal is to find the key that maps these M's to the C's. In other words, our goal is to find the key that maps M1, M2, M3 into C1, C2, C3. And as I said, our goal is to find the key that does this mapping. The first question is, how do we know that this key is unique? And so let's do a little bit of analysis to show that, in fact, just one pair is enough to completely constrain a DES key, and that's why this question makes sense. Okay, so let's see. So we're going to prove this simple lemma. Now let's assume that DES is what's called an ideal cipher. So what is an ideal cipher? Basically, we're going to pretend like DES is made up of random invertible functions. In other words, for every key, DES implements a random invertible function. Since there are 2 to the 56 keys in DES, we're going to pretend like DES really is a collection of 2 to the 56 functions that are invertible from 0, 1, 64 to 0, 1, 64. Okay, so of course DES is not a collection of 2 to the 56 random functions, but we can idealize the cipher and pretend that it is such a collection. Then what can we say? Then in fact, it turns out that just given one message and ciphertext, you just give me one pair, message and ciphertext, there's already only one key that maps this message to that ciphertext. So already, just given one pair, M and C, I can ask you, find me the key that maps M to C, and the solution is very likely to be unique. In fact, it's going to be unique with probability roughly 99.5%. I should say that this statement is true for all M and C, and the probability is just over the choice of the random permutation that make up the cipher. So let's do the proof. This is fairly straightforward. So what we're basically asking is, what's the probability that there exists some key that's not equal to K, such that, well, C we know is equal to DES of K comma M, by definition of C and M, but we're asking how likely is it that there's this other key K prime that also satisfies this equality. You realize that if this is true, if such a key K prime exists, then just given M and C, you can't decide whether the right key is K or K prime, because both of them work. Okay? But I want to argue that this happens with low probability. Well, so what does it mean that there exists a key K prime that satisfies this relation? Well, we're asking, what's the probability that the first key, the all0 key satisfies it, or the second key satisfies it, or the third key satisfies it, and so on and so forth. So by the union bound, we can bound this probability by the sum over all keys K prime, over all 56-bit keys, of the probability that des Km is equal to des K prime M. Okay, so we're asking basically, what is this probability for a fixed key K prime that it happens to collide with the key K at the message M? Well, let's think about this for a second. Let's fix this value. Let's suppose it's some fixed value. And then we're asking, how likely is it that a random permutation pi K prime at the point M happens to produce exactly the same output as the key K at the point M? Well, it's not difficult to answer and see that in fact this is, for a single key K prime, the probability is at most 1 over 2 to the 64. Right? There are 2 to the 64 possible outputs for the permutation. What's the probability that it lands exactly on this output? Well, it's 1 over 2 to the 64. And we're summing over all 2 to the 56 keys. So we just multiply the 2. We get 1 over 2 to the 8, which is basically 1 over 256. Okay? So the probability that the key is not unique is 1 over 256. Therefore, the probability that it is unique is 1 minus that, which is 99.5%. Okay, so already, if you give me one plain text ciphertext pair, the key is completely determined. There's only one key that will map that plain text to that ciphertext, and the question is just, can you find that key? Now, it turns out, in fact, if you give me two pairs, so you give me M1 and M2, and their corresponding outputs, C1 and C2, the probability, basically, just do exactly the same analysis, the probability basically becomes 1, that there's only one such key. Okay, essentially, this is very, 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 very close to 1, and basically it says given two pairs, it's very, very likely that only one key will map this pair of messages to this pair of ciphertexts, and as a result, again, we can ask, well, find me that unique key. And by the way, the same is true for AES. If you look at AES 128, again, just given two input-output pairs, there's going to be only one key with very high probability. So essentially now we can ask for this exhaustive search problem. I give you 2 or 3 pairs, and I ask you, well, find me the key. So how are you going to do it? Well, you're going to do it by exhaustive search, essentially by trying all possible keys one by one until you find the right one. So this is what's known as the DES challenge. So let me explain how the DES challenge worked. The challenge was issued by a company called RSA. And what they did is basically they published a number of ciphertexts, but 3 of the ciphertexts had known plaintexts. So in particular, what they did is they took the message here, the unknown message is colon, and you can see they broke it up into blocks. If you look at these are basically 8-byte blocks. 8 bytes, as you know, is 64 bits. Right? So each one of these is 64 bits. And then they encrypted them using a secret key. They encrypted all using the same secret key to get kind of 3 ciphertexts. So this gives us 3 plaintext ciphertext pairs. And then they gave us a whole bunch of other ciphertexts, C4, C5, C6. And the challenge was decrypt these guys using the key that you found from an exhaustive search over the first 3 pairs that you were given. Okay. So that was called the DES challenge. And let me tell you a little bit about how long it took to solve it. So interestingly, in 1997, using an internet search, using distributed.net basically, they were able to search through enough of the key space to find the correct key in about 3 months. You realize the key space has size 2 to the 56, but on average you only have to search through half the key space to find the key, and so it took them 3 months. Then kind of a miraculous thing happened. The EFF actually contracted Paul Kocher to build special purpose hardware to break DES. This was a machine called DeepCrack. It cost about $250,000, and it broke the next DES challenge in only 3 days. Interestingly, by the way, RSA said that they would pay $10,000 for each solution of the challenge, so you can see that this is not quite economical. They spent $250K, they got $10,000 for solving the challenge. The next thing that happened is in 1999, RSA issued another challenge, and they said, well, you got to solve it in half the time of the previous solution. And so using both DeepCrack and the internet search together, they were able to break DES in 22 hours. So the bottom line here is essentially DES is completely dead. Essentially, if you forget or you lose your DES 56-bit key, don't worry. Within 22 hours, you can actually recover it. And in fact, anyone can recover it. And so DES essentially is dead and no longer secure. And just kind of a final nail in the coffin, as hardware technology improved, there was another project called Copacabana. They used FPGAs, just off-the-shelf FPGAs, only 120 FPGAs. It only cost $10,000, and they were able to do an exhaustive key search in about 7 days. So very, very cheap hardware, just off the shelf. You can break DES already very quickly. So the lesson from all this is essentially 56-bit ciphers are totally, totally dead. And so the question is what to do. People really liked DES. It was deployed in a lot of places. There were a lot of implementations. There was a lot of hardware support for it. So the question was what to do. And so the first thing that came to mind is, well, maybe we can take DES and we can kind of artificially expand the key size so we strengthen it against this exhaustive search attack. And the first idea that comes to mind is basically, well, let's iterate the block cipher a couple of times. And this is what's called triple DES. So triple DES is a general construction. Basically, it says the following. Suppose you give me a block cipher E. So here, it has a key space K, and it has a message space M, and an output space, of course, M as well. Let's define the triple construction, which now uses 3 keys. And it's defined as follows. Basically, here, the triple construction uses 3 independent keys, encrypts the same message block as before, and what it does is it will encrypt using the key K3, then it will decrypt using the key K2, and then it will encrypt again using the key K1. Okay, so it's basically encrypting 3 times using 3 independent keys. You might be wondering, why is it doing EDE? Why not just do EEE? Why do we have to have a D in the middle? Well, that's just for kind of a hack. You notice what happens if you set up K1 equals K2 equals K3? What happens if all 3 keys are the same? Well, basically, what would happen is one E and one D would cancel, and you would just get normal DES out. So it's just a hack so that if you have a hardware implementation of triple DES, you can set all 3 keys to be the same, and you'll get a hardware implementation of single DES. Of course, it'll be 3 times as slow as a regular implementation of single DES, but nevertheless, it's still an option. Okay, so for triple DES, in fact, now we get a key size that's 3 times 56, which is 168 bits. So this is 168 bits is way too long to actually do exhaustive search on. That will take time 2 to the 168, which is more than all the machines on Earth working for 10 years would be able to do. Unfortunately, of course, the cipher is 3 times slower than DES. So this is a real problem with triple DES. Now, I want to mention that, in fact, you might think that triple DES has security 2 to the 168, but in fact, there is a simple attack that actually runs in time 2 to the 118, and I want to show you how that attack works. Okay, so, but in fact, 2 to the 118 is